Okay, this is going to be a discussion of section 16.7. Going to be looking at a concept called entropy. Entropy is going to be a quantitative measure, and while the book says it's a disorder of the system, really a better way to look at this is going to be it's an increase in the number of possible states. The reason I say that is that disorder, if you look at, say, putting a sugar cube inside of a cup of coffee, um, it's not necessarily uh, a way of looking at disorder. You might think of the disorder as being how does the sugar cube mix in? How does it change shape when it gets into the coffee? Rather than look at it in terms of disorder, I would rather you look at it in terms of how many different ways can a sugar molecule, once you put it into a hot cup of coffee, how can it position itself within that coffee? The opportunities become quite a bit more abundant once that happens. Um, so that's how I prefer you to look at it. But the entropy change in a reversible isothermal process is going to be the change in entropy is going to be equal to the amount of heat divided by the temperature, where again, temperature is going to be measured in Kelvin. You can state the second law in terms of entropy. And the entropy of an isolated system may increase, but it can never decrease. And when a system interacts with surroundings, the total entropy of the system and surroundings can never decrease. So if we take a look at the section, the main themes here have already been described. What I do want to draw your attention to is going to be an equation. In other words, this. To introduce the concept of entropy, let's consider an infinitesimal thermal expansion of an ideal gas. You're going to add some heat and then let the gas expand just enough so the temperature remains constant. Because the internal energy of an ideal gas depends only on its temperature, the internal energy is also constant. So from the first law, the work done by the gas is going to be equal to the heat. Work is going to be pressure times the change in the volume. We know how to write the pressure. And if we take Q divided by T, then this is the relationship we come up with. That's not going to change. This constant is not going to change. And therefore, the change in entropy is going to be the change in the volume with respect to the volume that we had before. And again, the entropy change is going to be the amount of entropy you end up with minus what you started with during a reversible isothermal process. So those are the main themes of this particular section.